Let's start this afternoon session. So Ramon Modoloy will just talk about insights into different bubbles and provide results.
Thank you so much. Hello everybody, welcome to the second session. And I want to start by thanking the organizers for inviting me. It's my first time in Bangalore and it's been a great pleasure walking around the institute and taking insights. So I'm going to talk in this session a little bit about galactic flows and what we can learn by studying it in our own local environment, namely the Milky Way. So let me start off. There have been so many great talks this morning, giving us some background and details about what we can learn about outflows and galaxies and so on. So let me start off by saying that galaxies are not closed boxes. Galaxies are complex, non-linear systems where gas flowing in and out of galaxies play a crucial role in their evolution over the cosmic timescale. For example, this is an all-sky image of our Milky Way galaxy. This is the stellar disk of the Milky Way. And we see around the Milky Way itself a huge amount of cold gas falling onto the disk of the Milky Way. These Magellanic streams will fall onto the disk of the Milky Way in a half a gigayear or a gigayear will provide the fuels for next generation of star formation on our Milky Way. Again, there are supernovae that are going on which are driving material out of the disk of the Milky Way and carrying it out into the surrounding galactic medium. So this kind of a quasi-equilibrium process where gas flows in from stars, something happens, gas gets ejected and somehow regulates the star formation rate of the galaxy. Basically drives what a typical galaxy is formed and lives in life cycle. This perhaps could be characterized by just looking at the color bimodality diagram, which is from a Sloan Digital Sky Survey. So every single dot on this plot is essentially a galaxy. And along the x-axis, I'm showing in this direction lower mass galaxies, in this direction higher mass galaxies. And along the y-axis, colors of those galaxies. Showing here, if a point resides here, it's basically more star-forming galaxy. If there is a galaxy here, that is less star-forming. And in the last 20 years, what we have learned about galaxies is that they primarily reside in two loci in this plot, primarily as blue star-forming clouds of galaxies or as red and dead passive galaxies which are no longer forming stars. The process by which they migrate from being a star-forming galaxy to a red galaxy is still unknown, and perhaps outflows or ejected feedback play a very crucial role in migration of a galaxy from this cloud to this cloud. Any basic model of galaxy formation needs to evoke some sort of outflow model to actually explain this transition, even to explain basic discrepancies between theory and observation. Here again, on this plot, I'm showing co-moving volume density of objects in the sky, basically. The blue curve presents the mass function, i.e. the number of galaxies per unit co-moving volume as a function of stellar mass across the Sloan Digital Sky Survey. And the red curve presents the co-moving halo mass density of dark matter halos from the Magellan acceleration. And you see that discrepancy that you see, it could only be explained if you evoke some sort of supernova-driven feedback at this low mass end and some sort of AGN-driven feedback at the high mass end. We have seen already so many studies about outflows. So we do know that outflows do indeed take place, be it supernova-driven, be it AGN-driven. The last few talks have elucidated that point dramatically. What I want to stress is that most of the studies of outflows that are taking place at high redshifts, you suffer from the fact that they only cover a small part of the sky. So what you end up doing, you put a slit on a galaxy, take a spectrum, and you use the starlight from the galaxy itself to look for blue-shifted or red-shifted absorption in the foreground. And that allows you to measure the kinematics of the outflow itself. However, because these are small sources of the sky, so it's very, very hard to get spatial information of the outflows. Sylvain presented some beautiful example of local galaxies where you can start to do 2D distribution of the gas and kinematic properties of these outflows. However, I argue that just by going even to a local source, the Milky Way itself, which basically covers the whole sky, right? We can actually leverage our vantage point in the disk of the galaxy to study the outflow in far more precise detail. And if you look at the Milky Way, again, this is a map of the Milky Way in gamma ray. This is the stellar disk. We know that there is excess emission in gamma ray, which is going towards the center of the our galaxy. This is the galactic center, and we see that there are plumes of bubble. Basically, there are two bubbles of excess gamma ray emission which are coming out, which are giant balls of plasma of hot gas, which is going out of the Milky Way, which aptly named as Fermi bubble because they were discovered by the Fermi telescope. But these exist also in other wavelengths. You can see them in microwave, seen in the so-called famous WM haze, as well as polarized radio emission, seen in those giant radio lobes of emission. And hard and soft X-rays. This is a little bit vague in this image here, but you can see that where the galactic center is, there are excess emission in many different wavebands. And essentially, we have convinced ourselves that this multi-phase outflow that we see could probably be seen in the center of our Milky Way itself. And there are many different theories about how the Fermi bubble are formed and how the gamma ray haze that is seen there happens. Primarily, I'll just like to focus on two main theories that have been going around in the last few years in the literature. There could be a hadronic process where cosmic ray protons might collide with the heavier atoms that exist in a galactic wind, and which may give rise to gamma ray emission. And this could be some sort of a slower process of star formation, slowly building up the Fermi bubble as you see. Or it could be an electronic process where electrons are colliding with the cosmic ray photons with inverse quantum scattering and creating the gamma ray haze that we see. And this could be again driven by some sort of a shorter nuclear activity in the center of the Milky Way. So these hypotheses that have been presented in the literature have relied on the multi-phase emission maps of the Fermi bubble, but till date, until a few years ago, very little information existed about the kinematics of the gas itself. So we decided to set out and carry out an experiment, which Andy Fox here is a PI, and we'll talk more about it in the next few days, where we used Hubble Space Telescope, and we decided to see if there are indeed entrained material in the Fermi bubbles themselves. So the experimental design is so forth. We have a bunch of UV bright AGN sidelines which are piercing through the Fermi bubble, and some of the sidelines which will not pierce the Fermi bubble. So if there is indeed entrained material, which should exist in galactic outflows, as we learned from the previous talks, if they do indeed exist, we should see them as Doppler-shifted absorption signature in the spectrum of the background quasars. And indeed, if indeed there are sidelines which are passing away from the Fermi bubble, we should not see any such signature. This sort of will allow us to determine the height of the Fermi bubble, or indeed if there is any material inside or outside the Fermi bubble, which I've trained. Then we set out to put some control samples in there. We selected some stars, halo stars, with no distances from the galactic center, so that they are sitting precisely inside the Fermi bubble. So they are only probing half the path length as probed by the AGN satellite. So when you look at the spectrum of these stars, you better see half the effect as you see for the other guys. And then we moved on and selected a few foreground stars, which are complete control samples. And the trick here is you better not see any absorption signature there, which are Doppler-shifted. Otherwise, the whole experiment will fail. So with this setup in mind, we went and asked for Hubble Space Telescope time. Yes.
How do you find the distance of these stars?
So these are halo stars. Some of them are blue marginal Grant stars, or some of them are known with the astrometry. The distances are known.
So that like some of the things that was
Yeah, some of them could be 8, some of them could be 10 kilometers, but all of them have no distances. So with this, experimental setup in mind, we went to Hubble Space Telescope and got a bunch of time. So the green dots here are AGN sidelines, the red dots here are halo star sidelines, and the orange dots here are foreground star sidelines. So in this talk, I will focus on what we found about the kinematics in the northern hemisphere. The reason is twofold, primarily because we have both sides and we decided to tackle one at a time, and also because the northern side is relatively easy. If you know the galactic sky, you'll know that there are the Magellanic streams, which I just showed, will pass to the southern side right about in this direction. And the kinematic signature of the Magellanic stream is exactly same as you should see for Doppler shifted absorption signatures of the Fermi bubble. So when you do an analysis of the southern sky, you have to be extremely careful to tackle that. And we will talk more about it in this talk and how to tackle the southern sky. But for now, I'm taking an easier problem and trying to measure the kinematics of the nuclear wind in the northern sky. And so let me first focus on the 5 sidelines, which we know are exactly inside the gamma ray base of the Fermi bubble. And we know them for sure that they are indeed piercing the bubble as we know it. And what kind of kinematics do we see as you look at it? The first sideline is called the PS456. It's a rather interesting sideline where you have both gamma ray and X-ray excess. So there's a lot of hot gas in there. And then when we looked at what kind of UV cooler gas you might see in absorption, this is the kind of signature you see. So I'm showing here in this plot is along the x-axis is line of sight velocity with respect to us, and along the y-axis normalized flux. So the signature you're looking for is the color-coded blue shifted or red shifted absorption, i.e. you're seeing gas either going towards you or going away from you. This is exactly the signature you should see if there is a biconical outflow going out of the center of the Milky Way itself. Now, this is for silicon 3. So this is around 300,000 Kelvin gas.
What is the
30,000 Kelvin gas.
velocity?
The velocity shift is the line of sight velocity. And this is going to from around minus 250 kilometers per second to around 250 kilometers per second. Almost. And as we go, now I'll try to go along the vertical direction and see if there is any change in kinematics as we probe different lines of sight. Yes?
So, for the Milky Way stuff around V of 0, did you make like a cut? What was your cut?
So indeed, so we decided to make a cut of anything that is line of sight velocity of plus minus within 100 kilometers per second. We don't consider. We only look for anything.
So only
higher.
high velocity.
It is exactly high velocity
Okay.
absorption. So if there is any absorption which is going perpendicular to our line of sight, i.e. projected velocity is 0, which will be in the central part. But because this is also the velocity at which the ISM gas will reside, so it's ambiguous for us. So for this analysis, we're just going to ignore. We're going to only look for clean signature of bipolar outflow here, which we see. And then as we try to go vertically upward, you better hope that this is not a random high velocity cloud that is floating around. If that is so, this kind of signature should pop up everywhere. Whereas if as you go along and you see a very, very symmetrical signature of decreasing velocities, that will be a signature that indeed you're probing a radial profile of an outflow. Indeed, as we go to the second line of sight, you see that indeed there is blue shifted and red shifted component, but the velocities, line of sight velocities have decreased, which you'd expect as you're going vertically upward. The third line of sight is the red dot, which is a halo star. You better hope that when you probe that there is no redshifted absorption, because redshifted absorption is essentially probing the far side of the biconical outflow. And when we looked at it, there was a great relief that indeed there is no redshifted absorption here. And then as we go to the other sidelines, again we see the velocities are reducing as you go vertically upward, and exactly at the highest point, there is very little blue shifted absorption and absolutely nothing in the red side, which is telling us perhaps we're probing the edge. We're kissing. This line of sight is literally kissing the edge of the Fermi bubble itself. So combining these 5 sidelines, we can actually try to plot a observed projected velocity profile of a galactic outflow, which may be driven.
So presumably in assignment we didn't see absorption towards the direction.
I beg your pardon?
What's the covering factor of the absorbing gas?
Oh, this is 100% within the Fermi bubble. I'm going to talk about it later. So the blue and red points are essentially, blue points are line of sight velocities, and red points are galactocentric center of rest velocity, i.e. we took out the rotation of the Milky Way itself. So as you see, these are projected velocities. As you go in higher latitude, the projected velocities are decreasing. And for some cases, you see two components, i.e. we're even decomposing, because we have good enough resolution, the different kinematic components of the outflow that you see in high velocities. And just to remind you, this is PDS 456. This is the first sightline that I showed. And as you go outward, there are five sightlines which are showing relatively decreasing blue shifted high velocities. Now, this plot I have shown is only showing silicon-3, which is probing around 30,000 Kelvin gas. But you should know that these sightlines are indeed probing multi-phase outflow, because we happen to be using UV spectroscopy, and UV part of the spectrum is very rich in terms of diagnostic power. We have several atomic transitions going from carbon 2 to carbon 4, which are probing from 10,000 degree gas to all the way up to around 100,000 degree gas. So within the next of temperature, we do indeed see a lot of gas. Then we went to Green Bank Telescope and obtained 21 centimeter emission spectrum, and at least for one sightline here, we do see a 21 centimeter emission, so even very, very cold neutron hydrogen gas is in there. For this sightline, there is absolutely nothing, so it's completely ionized. So with this rich data set, we can go ahead and try to predict what is the projected velocity that we might be seeing. To do that, we invoked a very, very simple model, where I'm assuming that we're sitting here and the galactic center is here. I'm launching a lot of gas clouds vertically upward. We're imposing the ansatz that we know the opening angle of the Milky Way's outflow, which is given by the X-ray bicone. With that, we can invoke different flavors of outflow model, as Norman described. And here the color is basically tracing the line of sight velocity that we will observe for an observation. The weird shapes are not a bug in the code, rather they are probing the projected velocity along the line of sight and the rotation of the Milky Way itself. So with that, we can try to probe what kind of velocity ranges are allowed by this model. So I use primarily 5 flavors of very, very simple outflow models. First, I presume there's a momentum-driven wind where gas clouds are being ejected from the center of the Milky Way in an elastic fashion. I know that's not very realistic, but it's a thought on the head. Those are given by the blue lines here for 2 different flavors of momentum-driven winds for 1,000 or around 1,300 kilometers per second. Then I assume, what if an Eddington luminosity agent shown a few megayears very quickly, and what happens then? That is given by this red curve here, and then I assume, what if there is a very, very simple bomb going off at the center of the Milky Way, like a set of point source explosion, which is given by the green line here. And the next hypothesis I tested was also, what if there is a central circular zone where it's constant star formation, which is driving the outflow out there, which is given by this dashed line here. These lines are showing where the absorption lines reside, and along the x-axis, I'm actually showing the opening angle that the projected line of sight will make as it pierces through the opening, the Fermi bubble. And this is giving, the hashed region is basically giving you what is the opening angle that we get from the X-ray bicone. Where this intersect is the region where our solutions are valid. And simply by looking at several solutions, we can see that we can immediately rule out specifically these models here, which are telling you that you should have extreme high velocity wings of minus 400 to 600 kilometers per second, which is not seen by the data. It's very, very simple, but you can basically convince yourself just staring at the kinematics that this kind of kinematic structure is consistent with a momentum-driven wind being launched at around 1,000 to 1,300 kilometers per second. So what does it tell us? Because we have constructed a model, I know exactly where the absorption is happening. So I know the radial distance of the absorbing cloud from the center of the Milky Way. So I can actually create the radial profile of velocity as a function of scale height. from the center of the Milky Way. And once we know that, we can integrate this profile, and I can actually give you a completely independent kinematic age of the Fermi bubble, which turns out to be around 6 to 9 megayears. So, what does it teach us? So, many other studies have done emission line maps, and they have developed different models and derived age of the Fermi bubble to be from a few tens of megayears or few megayears to few hundreds of megayears to gigayears timescale. So I cannot still tell you what is the origin of the driving mechanism that is populating the Fermi bubble. But I can give you this, that whatever it is happened very, very short time ago, or less than 10 megayears ago. So this tells me that, we can pretty clearly rule out any model that is predicting a slow secular evolution of the Fermi bubble by slowly building it up over hundreds of megayear timescale. So again, going back to the question that Norm asked, what is the incidence of high velocity cloud inside and outside the Fermi bubble? So is it just a fluke that we happen to find these satellites, and that if you look everywhere you'll see the same feature? So we tried answering it. So in the normal satellites, initially we had a few satellites which are definitely inside the Fermi bubble, which I showed, and we had a few satellites which are definitely outside. So when I initially looked, we found that all these satellites were not showing any sign of high velocity cloud, but one. So just slowly going through them. So only one satellite, this guy had a high velocity cloud. Other than that, none of them showed. So that was great. Initially I thought, hey, 5 out of 6 and 5 out of 5. So that's a clear difference between covering fraction. Now this is a small number statistics. And we know that there are way more quasar satellites than this. So what we did was we went back to literature and tried to find all the possible lines of sight that exist in this regime. So we ended up with around 47 lines of sight. 5 of them, which we put in our survey, are clearly inside the Fermi bubble because we designed the survey in such a way. Any other sightlines, there are around 34 sightlines which are outside, and there are around 8 sightlines which are in this gray regime, which may or may not be placed in the Fermi bubble, simply because we don't have the angular scale to differentiate them. Now, when we try to find out how many of them actually show high velocity clouds, so no matter how you slice and dice, we try to do it in different ways. We did a very careful job in that. And the bottom line is, there is a substantially higher incidence of absorption inside the normal Fermi bubble as compared to outside. And we are extremely convinced with these results, so we went ahead and did a press release, and we said that we can safely claim that the kinematic age is less than 10 nanometers. And that's a solid number coming completely independent of any other emission measurements. Now, there are some fun things you can do with it. Because we know how the line of sight is going, where it is going, we know the velocities. So, and for one satellite at least, we have an H1 measurement. So we know the velocity. For those satellites, we have different species. For example, we have silicon 2, 3, 4. We don't have to do ionization correction. We can just sum it up and say this is the floor number of atoms that might exist. We do a very conservative magnetic correction, and we can work out what is the mass outflow rate for such an outflow. Again, it's a floor number. And that turns out to be a mass loss rate around 0.2 to 0.5 solar masses per year. Now, we know the kinematic age of the bubble, so it turns out, assuming that there is a constant mass loss for the last 6 to 9 megayears, the total mass of cool gas contained in the Fermi bubble could be as much as a few million solar masses. And then we can take these numbers and compute what is the total kinetic energy associated with the bubble. Surprisingly, which turns out to be a number consistent with other studies which have used emission measures to compute the total energy of the bubble. So it's pretty self-consistent in that sense. So,
Why were you scaling to 200 kilometers? Why were you scaling to 200?
This is, I think this is for a quasar absorption study that Nicola did, and we're just using a scaling relationship, and you can change this.
I should be putting it down.
Yeah, that's true. So I will go back to this sightline quickly, which is the only sightline at this latitude which actually showed 21 centimeter emission, which was a surprise to us. So because we do have a very decent H1 measurement and we have O1 measurement for this sightline, we can do a pretty safe lower limit estimation of the metallicity of the gas, which turns out to be at least 30% solar or higher. We cannot give a stringent number simply because a lot of the ions are saturated. This is life. The other sightline that was a halo star, people have done metallicity measurement on that, and they have found that that is solar metallicity. And they have a much better handle on it because they have fused data, which gave you access to the Lyman series lines. Unfortunately, we don't have that in the HEC course. Now, this sightline was rather interesting. So we went back and tried to map out what kind of H1 emission you can actually see there. And we got green bank time with director's discretionary time for about 8 hours. And we mapped out that there is indeed a cloud structure there, which is bigger than the pencil beam side of the quasar itself. That got us excited. And also, it's a 1 square degree field, so we thought, hey, there might be a huge swathe of clouds that might exist there. So we went back and did a much bigger program of around 80 hours. And we did a big map of the sky there. And what it turns out that, no, that is not true. There is indeed one cloud, only a one small cloud that exists there, which is bigger than the pencil beam of the quasar itself. But and just to orient yourself, galactic center is vertically down. There is a very, very good signature that there might be a head-tail structure, which is showing that it might be entering gas which is vertically going upward. Why it exists, why there are no other gas clouds there, I still don't know. But this is a very tantalizing preliminary result we have on this, and we're hopefully going to publish it very soon. So with that, I will summarize the findings we have. We have shown definite detection of Milky Way's nuclear wind with Doppler signatures. We predict that the alpha velocities could be in the range of 1,000 kilometers per second. And that implies that the kinematic wind age is less than 10 million years. And I would argue that we have shown the first kinematic map of wind velocities for our Milky Way galaxy. And we find that the mass alpha rate could be of the order of 0.2 to 0.5 solar masses, just in the center of the Milky Way. And we know that the star formation rate of the Milky Way itself is around 1 solar mass per year. So it's an eta of around 0.5, just assuming the center of the Milky Way itself. And I thank you for your attention.
Time for a few questions.
So you're making quite a strong statement. I mean, I would agree with you. I've worked on a star formation scenario, and 6 to 9 million years would basically rule it out, I think.
Yeah.
But that you said that's the travel time from the Milky Center. So I guess I don't understand your kinematic analysis well enough to understand whether that really is just could it be an internal flow within a structure which is expanding much more slowly?
That's a good argument, but the point is, if it is an internal flow, you might argue that there might be other internal flows which has gone before and came down. We don't seem to see those structures. It's a very self-consistent structure of biconical outflow. There doesn't seem to be any other velocity components.
No, but you could have a nuclear outflow, right, which has a systematic.
Sure. So, okay, fair enough. This is an ansatz assuming that this is all entrained and everything is going together.
Okay.
There is no delay. Yes.
So I'm interested in the metallicity. So you got about a third solar.
Yeah.
And that's fairly robust, but it might be this weird little HBC thing. Is that right?
Yes.
Okay, so one thing that's interesting is if it is 6 to 9 million years old, then you think about the metallicity of gas in the galactic center, 6 to 9 million years ago is roughly solar, maybe even more than solar.
Yeah.
But is that then telling you something? I mean, that it's a third solar versus solar, maybe if it did come from there, is it then diluted? Does that tell you something about metal mixing?
Yes.
Or
Just a caveat, this is a lower limit. Because the lines are saturated, we could only tell you it's at least third solar, it could be higher. Then the other side, the Halo star, which is the Microsoft group, like 2008 or something, they found their solar metallicity at a higher latitude. So it just could be that we're...
So it's just a lower limit.
Just a lower limit. So, or it could be dilution, but I don't know. There's no way to tell.
I have to say, I find your absorption line study unconvincing. It's only a few sightlines. The interstellar medium, the circumgalactic medium might be complex. You might even, with a few sightlines, you might even hit maybe a nearby galaxy or something. So, and then you connect these few results from few sightlines to a very schematic galactic wind model where you have just shown that it's a multi-phase outflow.
Sure.
So how can you defend yourself?
So three points I'll try to argue in 3 stages. Number one, it is few sidelines. Those are the Evobrite phases we have. We have the southern side where Andy will present. So you will be shown that it is actually consistent on north and south. Secondly, if it is indeed, well, we have absolutely ruled out that this is some interloping absorber. We have identified all the associated lines in those quasar spectrum. It is not associated with other things. That is for sure. Thirdly, we have ruled out any possible interaction with ISM because first, the LSR cutoff takes care of it. Secondly, we have also tried to model it by assuming halo lag and like what kind of deviation velocities you could get and which regions can be ruled out. We have done it. Even after all this careful cuts, you see this. So we don't think this is ISM because the ISM stuff could be in the middle, but not in those extreme rings. Fourthly, we have also done a covering fraction analysis. So if it is indeed some random high velocity cloud floating around, there is no reason why the incidence inside and outside should be so dramatically different. So I think with those arguments, I would like to argue that this is we believe that this is inconsistent.
So you wouldn't think that more observations would be useful?
They're always useful, I would not say that. But I would just like to say that we have been very careful when doing this analysis. We were very, very wary of these criticisms.
We can continue this